Hello, community. So great that you are back. Today, we will leave the classical AI behind us and we will look, hey, what is the future of AI? So, we will go beyond our actual current AI models. Let's explore this future. Now, to do this, I have to explain here the classical AI. It takes about a minute and I will use some special code. So, we are all based in our AI models on next token prediction, NTP. It's very easy to explain. You have a sentence, the cat sat on there, and now the LLM doesn't just output a word. Internally, the large language model outputs a probability score for every single word in its vocabulary. Let's say we have about 70,000 plus tokens. So for the contents the cat sat on there, the output might look like, for the word mat, an 85% probability. For the word floor, 8% probability. You get the idea. Now, if you code this, and it's not a simple Python or C++ code, but we go for the code behind the code, and yes, of course, it's mathematics, this is a simple form that determines here the current state of AI. No? And the objective here, the objective function here is, of course, to maximize here the logarithmic likelihood of the text corpus given here a particular information sequence, and we optimize here the parameter theta of our large language model. Now, if you're not familiar with this notation, never mind, I'm going to explain it here. Very simple. J is our objective function for NTP, so we just want to adjust the model parameter theta, for example, our 671 billion free trainer parameter, to make this J score as high as possible. It's an optimization problem. Then, of course, we have here the summation, so we do here the calculation for every single token in a given sequence, and we have here a log probability. We take the log here of the probability simply for numerical stability. And then comes the interesting part, now our conditional probability calculation of the correct next token in a sequence. So what we take the actual token x at the position t from the training data, and then we have here the context. And the context is simply the input, if you want, all the tokens that came before this particular time interval. So all whatever was learned before. And then we just calculate the probability by our large language model with its current parameter theta. Very simple mathematical expression, a code that we use not for an assembler, but for our human brain to understand the basic guiding principle of AI for next token prediction. Now, as a human, you could say this formula expresses more or less the following. You go through every token here in the text that you're given to understand, to learn, and for each token you use the model to calculate here a particular probability it assigns here to the correct token. And the goal is here to tweak the model's parameter theta to make the sum of these log probabilities as high as we can possibly get it across the entire training dataset. And then we achieved it, because then we have trained an LLM with the parameters theta to do the prediction of the next token. And by maximizing now this objective function, the model is simply forced to learn the intricate patterns of the human language to become an excellent predictor of the next token. That's it, and that's how we do the pre-training of almost all our AI models. Now, if you look at the code in a little bit more abstract way, you understand what we have is more or less a simple configuration where our objective function with the parameter theta of the LLM is more or less an operator. So yeah, we are moving a little bit now to operator algebra and mathematics over the complete data set, and then we have here something like, we can call it a score for a single item. So one of the interpretation in the current AI system is here this objective function that outputs here not a single word like you might assume, but it outputs here a probability distribution, and we calculate here the maximum. It's an optimization problem. But we could also say, hey, what about this one? Huh? Now, we just change here the operator here over the complete data set, and we say E for an expectation operator. No? Let's say it averages your score over random actions here for our particular model. And then we have a reward function. So you see, it's very similar in the basic understanding here of the code, how to build here the next step. So we go for a next token prediction model here to a reinforced pre-training model. Now, just having here this operator and having here an optimization function is not enough, because we do have to have the real optimization procedure. So the question is, how do we optimize now J? Now, it's easy, no? You notice here, gradient of the objective function here with respect to the policy parameter is simply nabla theta of our objective function. And the most famous result, or if you want, in all the reinforcement learning, is kind of a simple policy gradient theorem. And here exactly is the way we calculate nabla theta of the J von theta. And here we again have here our operator over the data set. This is now a very specific expectation operator. And then we have the famous two terms. No? Now let's have a look at this, because it's really important that we understand it here on a deeper level, because we're going to code here an extension. So the first term here, this is our R, is our reward. And you say, hey, I know this. No, this is very familiar. Yes, of course you know it. Anyway, the first term is simply the total reward from over the trajectories, a sequence of states S and an action 8. Great. But the second term is now the interesting term. Now, this is the steering term, if you want, or the assignment term, whatever you call it, never mind. Because here we have our log probability of taking here a particular action A, given the state S of the system, and you have seen it, the nabla theta, this is nothing else than our gradient. So this tells us here for a particular solution for an optimization problem, hey, in which direction of the parameter space I have to move, either to enforce here or to reduce here a particular behavior. And this is it. If you multiply these two terms, you have it. Now, reinforcement learning is now one of the main paradigms in AI. And currently reinforcement learning with rewards, yes, but we have also verifiable rewards. This is particularly helpful. And we have here our objective function J. J, by the way, comes here from the coast control function. So we go back here to the 1950s in the notation. And now for reinforcement learning with verifiable reward functions, we have now absolutely the same basic code, if you want. Yeah? We have here an expectation operator. We'll have a look at this in a second. And we do something here, and this is here simply a reward function over an action A at a particular state of the system, producing here an output O. And for this particular set of question-answer pair that we have here in our training data set, in our labeled curated data set D, our question and answer, we have now the possibility that we generate now, given the policy of our LLM, and given here the question as an input, and now we generate here over this sample here an output. So what we can do, we can say, okay, this is now the new output here from pi theta. And I also have the ground true answer, the golden answer. I can compare those pairs. I can calculate the reward function. In the simplest case, this is either 0 if it's wrong or 1 if it's correct. And then I have it. It's as simple as this. No? Now, you know that the main problem currently we have with the verifiable reward option optimization is we have to have a label, human curated data set of really domain-specific question-answer pairs to really have a strong reinforcement learning. And the quality of the data, the amount of the data, the complexity level that should increase in our training data set, all these are problems that take a long, long time if you really go here and you have a humanly curated, and the synthetic are not really that good. And now here we have a new study, June 9, 2025, Microsoft, Peking University, and Tsinghua University. I always say Tsinghua is kind of a Harvard, and they tell me, no, we want to be MIT. So, okay, whatever you go for. Yeah, and this is here the cherry cake publication, and you immediately understand why. Now, it is easy. I just want to show you that you don't have to read 15 pages of research to understand an idea. You can have the abstract level of this idea in code, but not a simple Python code, but in the code behind the code in mathematics. And this is like we as a theoretical physicists, we analyze system. And AI is nothing else than a statistical system now. So this is a straightforward road. So what we have a basic equation. J, our cost function if you go from the control system, or our objective function if you go for the optimization here in computer science, is simply here an expectation operator that operates here on a particular set of reward functions. That's it. Objective, reward, expectation operator. Now, what is our goal in reinforcement learning? Maximize the expected future cumulative reward. That's it. So again, we have an operator algebra operating now over all of the system. The expected future reward functions provide us this, and this is simply the way to optimize the system. Now, this particular operator now in this new publication that we're going to talk today has some dependencies and some new ideas. And you see, this is the complete explanation of 15 pages of exactly, if you want to go back, this paper. You don't have to read the paper. If you understand the code, the mathematical code, you say, hey, this is now fascinating. If you don't see it, never mind. I'm going to explain it in detail, and you're going to laugh in about 2 to 3 minutes time how simple it is to understand this. So, you see, basic equation, just the expectation operator, and yes, the reward function. We will have a closer look. So if you want here the reinforcement pre-training objective, the objective function J here is now calculated in a different way. And is calculating now the expected reward, which is the average reward over the model we will get across all possible text samples and all its possible reasoning attempts. The goal of the training is to adjust the model parameter theta to make this expected reward as high as possible. So again, we are in an optimization structure. Now, what does this exactly mean? Let's have a look here. Yeah, let's start here with this term. Now, just have a look at this. If you know already, skip ahead. If you're not, simple explanation. This pi theta is nothing else than the policy. This represents our large language model itself. It is also, if you want, the agent or the decision maker that we are now training to perform a particular task. No? So this policy pi theta is, if you want, the brain. It's the brain here of the agent is, of course, the LLM. So it is the function that looks at the current situation. It knows here its own state and simply decide what of the multiple actions that's possible to take next. And the subscript theta represents here the specific parameter of our large language model. Billions and billions of numerical weights and biases in the neural network that are adjusted during the training. And you know, this is our main purpose. Find the perfect theta. And here now, if we go here to this notation, if we understand what is pi theta, this is here the given part. This is here our input. No? This is the given part of the statement. So X represents here the sequence of tokens. If we talk about human text, then this is the text from the training data. And the subscript here, less than t, means all tokens that happen before the current time step t. So if you train on 1,000 books, those are all the tokens from those 1,000 books, because what you want, given here this input, you want to hear an output. And this is a mathematical notation, but we're saying, okay, given this input, what is the output? So X is now, if you want, the context or the prompt. It is all the text the model has seen so far, upon which it does now its next decision, the output dot. Vertical bar is often called conditioned on or given, depends what you like here. And the dot is here a placeholder for the sync that we want to predict. And if we want, it kind of represents here the action, or we can also say the output of the policy. You see, it's rather simple to understand. And the probability distribution over all possible outputs, given here a specific input context X, is now defined by our model policy or by the LLM itself, pi theta. So you see, the meaning of this is all of this, so you see how effective and shorthand noted is a mathematical notation. Now let's come to the second term that we have in our expectation operator. No? So we have this term we just explained, and then we have here the tilde symbol. So what it means? It simply means we are sampling from this distribution. So we know that this is a probability distribution. Now we are sampling something from this. So what are we sampling? Let's have a look now at the complete term. You have here O. O stands for output, but we sample now G. As you see here, it runs from I equal 1 to capital G. We sample G different outputs from the probability distribution defined by our LLM model, our policy pi theta, when it is given the specific content X, or the history of the token, the history of the sequence, where each output O is now here a reasoning path, or if you want, a chain of sort argumentation and a final prediction. So you immediately understand, hey, wait a minute, this is now completely different, no? To everything that we know. We have now a reasoning path suddenly when we have here a pre-training. So we bring the idea of reinforcement learning from the classical idea of pre-training, supervised fine-tuning, and then alignment with reinforcement learning by human feedback. We shorten this, we mix it now together, and we have here the chain of sort reasoning path from the reasoning models now implemented in the very first element of the pre-training, how we predict with reinforcement learning the next token. So we built something completely crazy new. And this is simply the mathematical notation. Everybody that understands here the theory will tell you, this is the mathematical notation. And this is the way how you then code in Python or C++ or whatever you prefer. So you could say now, so we use our current AI model, the strategy pi theta, to look at a given context X before the time period T, and generate G different possible outcomes O, where each output here is a reasoning path and a final prediction. So you see, we create something completely new. It is not anymore just a simple probability distribution, but we have complete reasoning paths. So if you look now at the expectation operator that works now on all the possible reward structures in our optimization topic, we have now, if you want, two parts. Now, we have now rule 2. This is what we just looked at. Now, and we said, yes, we understand now what this mathematical notation means in simple human words. And now we have to look at the first part, because here is also absolute. This is here, if you want, the even more amazing part here of this operator algebra. The model tells us now here, hey, I don't want to rely here on a small training data set of curated question-action pairs with verifiable reward structures, but I want to go out in the world to annotated the web text corpus, the internet itself, and I say, this is my playground. No human interaction, no really carefully selected data sets. I just go out and I learn from the internet. And you might say, my goodness, all the nonsense here you find on the internet, yeah, let's do this. And the authors tell us this is our breakthrough idea. So a single rule now, this rule now, I'm going to show you in a minute, solves now the scalability problem of reinforcement learning. It provides here kind of a way to get a verifiable reward function from the ground truth text across trillions and trillions of token and word without needing any human annotation or interactions. So if you want, it returns the entire pre-training data set equal the internet into a reinforcement learning playground. And if you are Microsoft, you say, okay, 100,000 GPUs and let's start up the engine. No problem. So interesting to see now this particular approach. But yeah, I told you here we have to talk about here what they call the playground. What is it? Now D is simple. No? This represents the entire pre-training data set, could say the internet. And D is here a massive corpus of text scrapped from the internet, of all the books, of your corporate sources, of internet sources, trillions of tokens. So And we sample this now. And what do we sample? We sample two parts. One is a context and one is a ground truth condition from those data. So what we do, for each training step at a time t, we randomly pick here a snippet of text from the entire multi-trillion token pre-training corpus and split it simply into a part of the context and a ground truth continuation, or simply a correct answer, or a grounded answer, or a true answer, whatever you like. So you assume that every sentence, let's stay with word and sentences, every sentence we extract now from the internet is correct and has a context and a ground to truth continuation, and there's no BS anywhere in the world. Great. If you see it through this lens, here, this is a breakthrough, no? Because it elegantly states that the ground truth text itself, meaning the internet, is now the source of the reward that we can verify. So if you want, it is kind of an algorithmic breakthrough because you can scale to internet-level data sources. It is free from any human annotation, and you have a general purpose idea you can train on every knowledge domain in the world. Let me give you an example. The cat sat on there, and now the model predicts mat. And the ground truth from the corpus here, from the internet, can automatically confirm that this is a correct, reward-worthy action. So if you think everything on the internet is true and correct, beautiful, then we achieved something. Then the authors tell us, hey, this is great. Because it takes here the greatest strength of a standard pre-training. This means we copied here the internet for cheap data and fuses it here with the power of the reinforcement learning we have been optimizing since 2017. So if everything on the internet is true and we have grounded truth and we can say this, then we do have now a reinforcement learning process for the pre-training of our new models. And you might say, but wait, for each and every token I have now a reasoning model like the O3 Pro that takes 7 minutes to answer how many R's are in strawberry. And now we do this in the training of the model that it learns the pattern, and we have now a pre-training model learning now reinforcement learning in the pre-training phase. Yes, exactly. Isn't this beautiful? Okay. Now, you see that our operator has here the second part. Now, and the actions that are now particularly taken are from a set of actions from a reasoning pool and not a simple mathematical probability distribution. This changes the game. So you might ask, hey, again, sorry, interrupt. Why is it different from a standard LLM action we have today with pre-training? Now, easy. The standard LLM action is a simple recipe. No? Given the context, our text, the cat sat on, pick a single next token. Let's say a token is a word. We have a specific tokenizer with the highest probability in our probability distribution. Let's say on the top of the probability Gaussian distribution, and sample this one. It is a direct one-step decision-making in the current AI models. And now we modify this. We say, given the context, first create a pool of G, you remember, I to G, different lines of reasoning about what could come next. So if we have the text, the cat sat on there, now we start a reasoning process. And now all possible interpolations and extrapolation and reasoning patterns and content influencer come in, and the AI starts to reason. So the entire pool of reasoning traces, like chain of thought, constitutes now your action for this step. And the resulting reward from all of these pool constitutes will shape now the learning to come to the same result. We predict now the next token, but not in a single process, but we have a complete reasoning process of the LLM. And at this point, reading this, I said, hey, wait a minute. But this is not pre-training, yeah? Because I have to use the complete chain of thought method in an existing large language model, in the simplest case, or a vision language model, for each single token, the predictive endeavor that we have here. So I have to have an AI model that already knows how to do chain of thought first. No? So I don't start from scratch, but this is now, if you want, a super AI model. No? And yeah, reading the paper, you will see, yeah, absolutely. So the authors especially called here the DeepSeek R1, and they took here a distilled Q114B model. And they say, this is our normal base model. This is the model we use to apply a chain of thought method now for the pre-training of the next single token prediction endeavor, where we have now a multitude of reasoning traces and chain of thought sequences in order to amplify and integrate here the reasoning skills of our models to predict the next token. But not in the standard way, but in this new way. So this model here, our Q114B, is now forced to use its reasoning skill. Remember, this is here distilled here from DeepSeek R1. So we use here the R1 reasoning skills for every single challenging token prediction. And this gets now a constant rewarded practice. And if you want, this is really, if you want a cognitive muscle being exercised millions of times. This is now the new learning paradigm. So this is now fascinating, because now you tell this model, you can learn ad infinitum. You can learn and learn and learn. And because we use a reinforcement learning, we are now interested here in the learning performance. And you might say, wait, you want to tell me suddenly, after all 4 videos where you told us, hey, I think last video, I showed you continuous learning is currently not possible. This would be a way out of the dilemma? So you can ask, hey, how did this 14B model learn continuously? Or did it just apply its static knowledge to do here this new reinforcement pre-training learning? And the answer is, I think the model learns really continuously throughout the entire OPT process. Why? I would argue in the following way. Given we have a specific textual context, no? This x sub less than t. So our model LLM, the policy pi theta, generates now its reasoning pool of g different responses, and each output is now a reasoning trace and a prediction. So this is the pure forward pass through our neural network. At this point, no learning is happening yet. The model is just performing based on what it currently knows. And now the automatic verifier compares now each of the G prediction, as I just showed you 5 minutes ago, to the ground truth answer A from the dataset, from the training dataset. And if the complete internet is correct, then it's an easy solution, because then each of the G reasoning paths is assigned a reward function, a reward R, a scalar reward. In the simplest case, it's 1 for correct and 0 for incorrect. And using now what we know as a GRPO, a policy gradient algorithm, our nabla theta on J, the system calculates how to change the model parameter theta. Our, 14 billion free trainable parameter, for example. And the algorithm's core logic is, for the reasoning path that led to a higher reward in our reinforcement learning for the pre-training, we just adjust here millions of weights in theta to make those specific paths more likely to happen again in the future, because this was a successful path. I want to have this in my memory. I want to have this representation encoded here in my weights and my biases. And for all those paths here in our G predictions with a chain of thought and a prediction that led to a low reward that was simply incorrect to the golden ground truth by the internet, adjust the weights in theta to make this path less likely. We do not want to see this anymore in our neural network. So this adjustment is done using here the standard mechanism of a backprop and a gradient-based optimizer like an Adam optimizer, and we achieved what we wanted. We wanted to modify here the tensor weight structure theta of our LLM. And now we physically change them. So we did create a new, slightly smarter model, theta dash. And the loop starts again with the next one. This is now a complete new view how to do pre-training given the experience we have with reinforcement learning. And I think the question is, how far can you go with this? Can you really go infinitely continuous learning with this OPT process? I think this is fascinating. Yeah, of course the authors tell us, hey, listen, it's a little bit much to calculate here, even if you are Microsoft and you have infinite amount of NVIDIA GPUs. So we do have to have some filtering. No, and simple. No? Most of the tokens in any text are very easy to predict. No? Normally, if you say the cat sat on there, you would assume that math is here highly predictable. So running now this really computational expensive OPT process on these easy tokens would be just a waste of computation, because you can be quite sure even a 14B model would immediately guess without OPT, just its normal pre-training, that math would be an answer to this given query. So what they did, they used the small proxy model to calculate now the entropy of a token. I have a specific video on this just last week, for each potential next token. And a low entropy means that the next token is obvious and easy. Therefore, we do not have to run the complete OPT process. Only when the calculation here for the token entropy is, hey, this is there's a high probability that we do not know this. This is a real difficult challenge, no? So high entropy means the next token is difficult and uncertain to predict, requiring now the real reasoning process of OPT. This OPT process is of course dependent on the quality of the chain of thought augmentation in this particular LLM. And if we have a 14 billion LLM only, and not the pure R1 power of 671 billion free trainable parameter, you see immediately another limitation coming in just from the quality of the LLM we use. So this expensive reinforcement learning based reasoning loop for the pre-training will only run here on these high entropy tokens. Absolutely fascinating. We go crazy in the computation overhead, but we include now single entropy token calculations for all the tokens in the pre-training test of trillions and trillions and trillions of tokens. And I think we are just going crazy. And maybe there's a much more elegant, simpler solution waiting out there for you. And I hope you will be the person to find it. But if you are Microsoft, this is the way with brute force power, 100,000 GPUs. Just go for it. Now you could argue, and this was a test that they performed, hey, the reasoning model would do better if we just let it think before predicting. So maybe we do not have to do this RPT training that I showed, what we ran through and then the loop and we still ran through and a loop and again. What if we just do the generation of the next token via a single chain of thought with no backpropagation, with no Adam optimizer, with no RPT? Would this also give us, 5, 10, 20% of improvement? And here you have, really from the publication, you see here, they calculated here on it is a sample, of course, on mathematical question, because there it is rather easy to say, hey, this is a correct answer, or this is a mathematical incorrect response. So from the held out validation set of 200 samples of a mathematical benchmark, they calculated here the entropy-based data filtering strategy. They categorized here the token position into easy, medium, and hard, whatever this means. Never mind, it's just your demonstration. And they showed us, okay, so the classical way, the standard next token prediction, we have here our QN 2.5, unfortunately not the 3, the 14B model. No? And you see 41%, great, 30% accuracy, 20%. And if we go then for the R1 distilled model, where we have the R1 reasoning traces helping now the Q140B to improve its augmentation, you see, not really happening here, okay? So, but if we have now this new method that we just talked about here in this video, And we have now the RPT 14B trained, pre-trained model. Then you see on the same task, instead of 41%, we jump to 45%. Instead of 30%, we jump to 33%. And instead of 20%, we jump to 23%. And then I said, yeah, great. This shows us that this RPT is working. But I ask you, hey, what about we don't do this RPT and we just have the reasoning process for the single next token? This is exactly this line here. We fall back to 3% and 1% performance because the model is not learning. The model is not pre-training on the new data. The model is just crashing down to 3%. So this means just more reasoning without learning is not a solution. You have the reinforcement learning and then the pre-training where the model learns, and then another loop of reinforcement learning and the pre-training where the model learns. Just reasoning, even if you have here a beautiful R114B that has a performance of 41%, if you apply just predict the next token, no way. Interesting result. Now, this thinking process, what is now happening in this thinking process? Now, you are not gonna be surprised if I tell you those are the reasoning traces that are extracted now from the R1 model from DeepSeek. So here an example. So we have a particular topic to predict the next token. We are an RPT, the 14B model. And now we listen here to the reasoning to predict the next token, which is crazy to think about this, but okay. So the sorts of the RPT14B are, okay, I need to figure out what is the next token. So let's think about what could logically come next in a text about calculating now the vector magnitude. So we have any query about a vector magnitude. Never mind, it's not important what is the task, it's just to understand here the reasoning pattern. So the AI says, hey, the flow so far is introducing the topic, explaining the formulas for a 2-dimensional and 3-dimensional vector scheme, and now moving on how to actually perform the calculations. Since the user mentioned go over sum, the next part is likely going to be, or alternatively it could be, and I imagine O3 Pro going here minutes on 1000 GPUs just in all possible directions. Common phrases after we can go over sum could be examples, steps, methods, looking at similar concepts in educational materials after explaining the formulas. And you might say, my goodness, what are you doing, AI? And the text goes on, but perhaps given the user started a new section, it might be a new paragraph. Wait, perhaps in the original, the next part was an example or an explanation. Let's think about this standard educational context pattern. So the entire text might continue as, but alternatively, perhaps the next line is also a new section. Wait, I have another idea, I have another approach. However, the original text could have a space before the next word. So wait, maybe looking here at the initial document, it is structures. I am using Markdown now for the headers, and you see what is happening in the reasoning process for predicting the very single next token with a reasoning model RPT in the pre-training of a model. And you might say, who came up with this absolute crazy idea of an extreme computational overhead methodology just to include the reasoning model to find a new commercial application for the reasoning models? And I'm going to tell you the solution, Microsoft. Because Microsoft, you remember, you have to pay for the input tokens, for the output tokens, and for the reasoning tokens. So isn't this a beautiful new income stream for a global corporation if they say, hey, you know what, we have a new pre-training methodology. But this was not the point to show you this. This was the point that I could show you if you can either read 15 pages here that are explained in a human language, or you are much more efficient. Like a theoretical physicist, like we have a PhD in mathematics, you can go to a code simplification, to a mathematical notation that explains everything. But you have to have a huge background knowledge of context. Because without the context, you will not be able to understand the mathematical notation. But if you do, you see a simple paper here by Microsoft and Tsinghua, one of the best universities in the world. You can reduce it to one single equation and understand it and the implementations and the implications of this. So, computer code is nice for an implementation, but mathematics is even better if you want to discover the next AI. I hope you enjoyed this. I hope I've given you an outlook and a feeling what is possible, what is coming next. Maybe not really the rather computational expensive idea of reinforcement learning for the pre-training of the next model. I mean, Microsoft can afford to implement this, but for all the other people in the world who don't have 100,000 GPUs, somewhere in your server rack, so I would say maybe not the optimal solution, but we are developing alternatives to the classical AI system. And I think this is the absolute fascination. We are starting to think outside of the box. We will go beyond the current AI. So if you want to see what's happening, subscribe, and I see you in the next video.